Good morning, we are Pinkster, and this is a presentation overview of our entire semester project. My name's Katie.
And Sanjor.
And I'm Caleb.
Today we're going to review previous information as well as focus on design for environment, product architecture, industrial design, design for future, and have an overview of all our economic analysis. This is our final Gantt chart. As you can see, we were almost done. All we have to do is submit this video and give a presentation on Wednesday. And as of right now, we are about a day ahead of schedule. To start off this project, we all were told to go and come up with our own opportunities. I focused on obstacle 1 and decided to focus on 8th grade and do an incremental improvement product. Caleb focused on obstacle 2, decided to design for 7th grade, and chose a derivative product. Finally, Sanjar focused on obstacle 3, focused more on 4th grade, and did a derivative product as well. In the end, we decided to focus more on 8th grade because it made it a little easier for us to come up with obstacles for introduction to physics.
For our product, we have 5 customer needs, which we rank on their importance. So our user-friendly customer needs has the highest score because that's very crucial for our product. We also have we have 5 specifications which include like the spring force and the height and speed, which we correlated with the customer needs to better understand which specifications we need to focus on.
For our concept generation, we initially started with this design with a loop-de-loop into a spring launch and then finally through the Planko, but then we later discovered that you have to start and stop at ground level. So we changed this design over to our iteration 1, which started with the spring launch, which then went through the Planko and then ended with the loop-de-loop. However, we ended up not getting to use either of these because the loop-de-loop kept not working for us, so we went ahead and switched it to a slanted ramp with an Arduino attached.
So as far as intellectual property goes, for the most part, there isn't a product like this on the market. There's a lot of similar things, but overall, this is a pretty new idea, making a kit like this. But some of the things we pulled from were like a Hot Wheel toy trackway that kind of launched it with the spinning wheels, projectile launching devices, so kind of like using a spring, kind of like Nerf guns. I think we addressed that. And then the main thing that we had to kind of worry about, though, was the Plinko game board. So it's a randomized game board, and that name itself, Plinko, is trademarked by a television show, The Price is Right. So we just had to make sure that we changed the kind of the design and definitely did not use that name in our final product manual because it is trademarked.
For our product decomposition, we have 3 inputs into the system and one output, and these inputs include the speed of the ball, the speed of the motor, and the power to power the programming in the Arduino. And we have a concept scoring chart, which we narrowed down 4 concepts to 1. We compared their ratings with our criteria, and we concluded that the D222 has the highest score. Except we couldn't choose the concept because we had to change some things, as Katie helped explain.
For our failure modes and effects analysis, we went through and discovered that the spring launch had the highest RPM and was most likely to fail because of the fact that it was very easy to have too much force or too little force on the spring setup, which meant that the probability of the ball actually getting into the Planko was very low. Besides that, the Plinko and the slanted ramp scored about the same because for the most part, they were relatively reliable as long as the ping pong ball made it from obstacle 1 to obstacle 2 without any snags. We then went through and thought about how our design would affect the environment. Our materials are mainly made up of high-density wood, poster board, and cardboard, all of which cause deforestation. However, that also means that they're recyclable, so you can go through afterwards, and when they dispose of it, they can shred it. So when we produce this, we will advertise that it is 100% recyclable. Production-wise, there'll be air pollution just from factories. For the distribution, there's going to be a lot of waste from all the packaging, and this can also be recycled. For our use, a main issue we had was the material abrasion, like the spring digs into the wood, and everything else will fatigue over a period of time. However, it's extremely easy to replace because we use such cheap pieces, and none of our cuts are particularly confusing. They're mostly squares and rectangles, so it's extremely easy to swap out a part. Recovery-wise, it's very easy to emphasize material recovery when you're working with cardboard and wood, because you just take the leftovers and you either burn it and use it for a fuel, or you shred it and use it again, or just use spare parts that are big enough for other pieces.
For product architecture, we have 4 chunks, and each chunk has 2 subsystems, and this image shows the relationship between each chunk and the subsystems. So this will help us to what to change for future similar products.
For industrial design, we went through and focused on the strong points of our project, one of which was ease of use. Our product is extremely easy to set up, partially because after all of our attempting to get it work, we had to take out a lot of the user interface. It also only requires the user to do one thing, and that's to extend the spring to launch the ball. After that, it all operates by itself. The emotional appeal was with the Plinko, and it applied to childhood and watching The Price is Right and going through physics and watching the balls change around and show the probability of them actually following the same course. Repairs-wise, as I mentioned previously, it's extremely easy to repair due to the fact that our materials are very easy and cheap to get a hold of. Our use of resources, we went ahead and used all recyclable resources except for the spray paint, which means that we will have an abundancy of the resource. For our product differentiation, we were one of the few groups that had a successful spring launch, and we were one of the only groups that used a Plinko incorporated into our project.
And this is our 3D model of our product. And it shows the 3 obstacles and the most important features.
So designing for the future, there's just a few things that we kind of thought we could definitely make improvements on if we were to continue this project for another semester. Mainly, as we kind of stated, was user interface. We kind of had to pull back from that a little bit, just in designing. Like, we wanted to make an adjustable loop-de-loop and have the students calculate how it would travel through that. And we just had to kind of take some of that stuff out. So if we were to redesign it, we would definitely try to work that back in, just so the students would have more learning opportunities. And then durability was a big issue because it worked fine while we were testing it, but when it got to the actual testing in class, we had a failure of the hinges that were used on the Plinko, and it collapsed in on itself. So durability, better materials. We were using pretty cheap materials, so I think for like a final design, if we use more expensive materials, it would probably be fine. And then broader customer needs, we did contact a lot of customers. We contacted about 8, but we only heard back from 2 of them. And that might have been when we emailed them versus like just going to the school and talking to someone. Or we could have like called the customers. And we just felt like if we could have gotten a hold of a couple more, then we might have been able to figure out what teachers were really looking for and help improve on our design. So then to start our economic analysis and kind of figure out where we were at to begin this whole project, we did like a rough estimate of how much this project would cost. And that was, I think it was close to about $80 to manufacture. And given that, we realized that we'd have to sell about 175, 176 to get a break-even point, and then after that, we would just increase in profit from that break-even point. So then we did a cash flow diagram, and this was just kind of to show what we were asking from VTEPs as far as an investment. And we separated it into a 3-year time period, and then we separated those into quarters. And then we were asking VTEPs for that initial investment during the first 3 quarters of year 1 to get us kind of started and to get the manufacturing going. And then in quarter 3, that's kind of when we start the initial manufacturing, so there's no inflow or outflow there. But then after that, we start having outflow and we start getting that investment back to VTEPs. And we kind of thought that in the quarters 1 and 3 of the years, we would sell more just because those are the start of school semesters. So the cash outflow is a little bit higher there. But overall, it's an increase in returning that investment back to VTEPs with a final IRR of about 29%, which we feel is a pretty high return on the investment that VTEPs initially gave us. So then we did an actual final cost once we were assembled and we knew what we were using to build this BRG. And then we also figured that employees, we would pay them about $12.45 an hour. So given the purchase materials and then assembly time for the obstacles and the different parts, and then machining was just kind of some of the things that we did and how long we thought we took to build those different parts, so like cutting the wood and machining like that. So we added those times up, and then we used those times with the cost for an hourly employee, added that up with the purchase materials to get a total cost of about $50 for this product, which was kind of lower than our initial idea, which is good. It's cheaper than we had initially planned, so that break-even point should be lower than we originally thought. So then just assembly times, which we used in determining the final cost. Obstacle 1 will take about 48 seconds. Obstacle 2, about 37, and then obstacle 3 is definitely the shortest with only about 9.3 seconds. And overall, this assembly time is about 1.5 minutes, just over 1.5 minutes, which we feel is a little fast, and it seems a little fast, but I think once you get in the rhythm, it's really pretty reasonable for just assembling it, because as Katie said, our design is pretty simple and not too complicated to get to put together.
In summary, our final cost ended up being about $50, and we finally decided on obstacle 1 being a spring launcher, obstacle 2 being a Planko, obstacle 3 being a slanted ramp. And if we were to continue working on this project next semester, we would increase the durability, like the failed hinges, and we would increase the probability from the spring launcher. Thank you. God, I hope it was still recording. That one's still recording.